Hey everyone, welcome to today's Explainer. We're jumping straight into the situation with the MV Hondius and looking at how a massive shift from biology to engineering is basically changing the face of public health infrastructure. You know, when news breaks about a rare virus on a cruise ship, it's so easy for the headlines to just lean completely into panic. But today, we're bypassing the fear-driven language entirely. Instead, we're going to focus on the structural vulnerabilities this event exposes and how this incredibly innovative concept called the computational respirator offers a grounded, solid engineering solution.
Here is our roadmap for today. We'll cover 1. The cruise ship cluster. 2. The confined space vulnerability. 3. Enter protective computation. 4. The physics of the mask. 5. Stabilizing a chaotic system. And finally, 6. Scalable and certifiable safety. Let's get right into it.
Part 1. The cruise ship cluster. Let's start with a strictly factual framing of the MV Hondius event.
So, looking at the numbers, right now we have exactly 7 cases. That breaks down to 2 confirmed cases and 5 suspected. Tragically, this has resulted in 3 deaths. This is out of the 147 passengers and crew who are currently instructed to just remain in their cabins while health teams investigate. It's a very serious situation for the folks on board, absolutely. But looking at the raw numbers gives us a highly specific, localized scope. We need a steady, rational tone here.
And the timeline of the outbreak really clears things up. Investigators believe the Andes virus, which by the way is actually the only hantavirus known to spread human to human, and even then only through super close contact, like spouses sharing a tiny cabin, well, they think it infected the initial couple before they even boarded the ship. It fits the incubation period perfectly. From there, we've seen targeted medical evacuations to South Africa and the Netherlands.
This actually lines up flawlessly with the World Health Organization's early assessment. They stated clearly that the event is serious but contained, and that the global risk remains low. Basically, there is absolutely zero evidence of sustained community transmission. What we're dealing with is a localized, high-severity, but incredibly low-spread pathogen.
Moving on to Part 2, the confined space vulnerability. We need to talk about structural amplifiers of rare pathogens. Because here's the real lesson we should be extracting from this event. Look at these specific environments. Ships, airplanes, dormitories, remote work sites. You probably find yourself in one of these on any given Tuesday, right? The structural vulnerability is that rare pathogens can escalate wildly when you put small groups of people into these confined spaces. The global risk might be near zero, but the local risk in a closed-off room, that can spike exponentially. The world doesn't need panic, it just needs better protective infrastructure for these exact environments.
Because right now, outbreaks like this expose a massive, gaping hole in how we protect ourselves. Think about it. In a lab, protection is tested in a perfectly controlled, predictable environment. But out in the real world, traditional masks are completely passive. They rely on perfect fit, perfect human behavior, perfect conditions, and let's be real, those things almost never exist in a sudden outbreak on a ship or a busy worksite. When the fit fails, the protection fails.
Which brings us to Part 3, Enter Protective Computation. We're looking at the Oikonomia approach.
So, what exactly is protective computation? Well, it's computation that actively reduces physical risk by making the environment more predictable, measurable, and controllable. Think of it as a stability-first architecture. It's not just sitting there passively crunching data after the fact. It's actively designed to stabilize chaotic physical environments in real time.
And they apply this directly to the Oikonomia Computational Respirator, which is built across 3 distinct layers. Mechanically, you've got a high-seal silicone facepiece with certified N95 or FFP2 filters. On top of that, you add a sensing layer packed with optical and pressure sensors. And finally, a computation layer that models airflow. Now, I want to be crystal clear on this point. This is not a diagnostic device. It does not detect viruses. It's purely an engineering and computation tool. A next-generation mask that enhances standard, certified respirators.
Part 4. The physics of the mask. Let's demystify exactly how this technology works.
There is no jargon or mysticism here, guys. It is just pure physics. Oikonomia literally uses light as a computational medium. There's no biological detection whatsoever. By using light to read the physical space inside the mask, it creates this real-time, deterministic model of exactly what's happening as you breathe. Here's how it actually plays out, step by step. As light patterns shift and evolve through the mask's materials, optical sensors measure the aerosol density. At the exact same time, pressure and humidity sensors are constantly checking the quality of the seal against your face. The system takes all this raw physical data and models the filter load in real time. It's always asking, is the seal tight? Is the air flowing correctly?
Is the filter getting saturated?
This naturally leads into Part 5, stabilizing a chaotic system. It's all about order emerging from complexity.
Now, think about human breathing for a second. When you combine breathing with airflow and microscopic particle movement, you get a highly chaotic, totally unpredictable physical system. So the million-dollar question is, how do you stabilize that chaos? How does this mask take all that complex, real-time modeling and actually give the wearer measurable, predictable protection? Because a ton of real-time data is completely useless if the person wearing the mask doesn't know what to do with it, right?
Well, it solves this by boiling all that complexity down into incredibly simple, actionable user feedback. It's a simple loop. Green means your seal is good and airflow is normal. Yellow tells you to adjust the fit or maybe get ready to swap the filter. And red? That means the filter is compromised or you need to get out of that high-risk area immediately. It detects the leaks, the poor fit, the saturation, basically stripping away all the guesswork and anxiety of wearing a mask in a dangerous environment.
And finally, Part 6, scalable and certifiable safety, building infrastructure for the future.
This is where we can really reassure the public, because the concrete engineering benefits here offer total certainty. It doesn't try to reinvent the wheel. It starts with standard, certified respirator performance like N95 or FFP2. Stuff we already know and trust. It simply adds computation to fix those real-world failure modes we talked about earlier, like a mask slipping off your nose in a tight space. Plus, it uses reusable hardware with replaceable filters. And importantly, because it relies on straightforward engineering pathways, manufacturing can be scaled rapidly and predictably if a crisis hits.
Which brings us to the absolutely critical takeaway we should all have today. The world is not facing a new pandemic, but we can build tools that make even rare outbreaks less frightening. Protection can scale exactly as fast as the threat, as long as we rely on grounded, transparent engineering instead of fear.
So that leaves us with a pretty fascinating thought to ponder today. If we can use engineering and protective computation to stabilize the physical chaos of breathing during an outbreak, what other fragile, chaotic human systems that you interact with every single day are ready for this kind of stabilization? It's a wildly exciting frontier for engineering. Thanks for joining me for this explainer, and I hope this gave you a much clearer, more grounded perspective on both the current situation and the amazing tools being built for tomorrow.